The capillary number, Ca, is a measure used to understand the balance between two types of forces in a fluid: viscous forces, which relate to how thick and resistant to flow the fluid is, and surface tension forces, which act like a skin on the surface of the fluid holding it together. In simple terms, it helps us predict how a fluid will behave in different situations. For example, in painting, blowing soap bubbles, inkjet printing, and mixing oil in water, the capillary number tells us whether the fluid's thickness or the surface forces will dominate. This concept is especially important in microfluidics, where tiny fluid systems are used for precise tasks like medical tests and chemical reactions, ensuring that droplet formation and movement can be accurately controlled. Two important forces are viscous forces and surface tension forces. These forces are constantly at work, shaping the behavior of fluids. Think of them as two teams in a constant tug of war. Each team has its own role and influence on the fluid's behavior. Viscous forces are like the sticky team, trying to hold the liquid together. They resist motion and make the fluid thick and slow-moving. They're what make honey so thick and slow-moving. Viscous forces are all about internal friction within the fluid. On the other side, we have surface tension forces, the clingy team. These forces act on the surface of the liquid, pulling it together. They act on the surface of the liquid, trying to minimize its area. This is why water droplets form beads on surfaces. Surface tension is why water forms spherical droplets. It's the shape with the least surface area. This minimizes the energy required to maintain the droplet. Now, the balance between these forces determines how a fluid behaves. The interplay between viscous forces and surface tension is crucial, and that's where the capillary number comes in. This number helps scientists understand the relative importance of these forces in different situations. By studying the capillary number, we can predict how fluids will behave in various conditions, from industrial processes to natural phenomena. So next time you see a droplet of water or a stream of honey, remember the tug of war happening inside. It's a fascinating dance of forces that makes our world so interesting. Thanks for joining us on this journey into the world of fluids. Stay curious and keep exploring the wonders of science. The capillary number, or Ca, is like a scorekeeper in this fluid tug of war. It tells us which force is winning, viscous forces or surface tension forces. A high capillary number means viscous forces are in charge, while a low capillary number means surface tension is dominating. Imagine a race between a snail and a cheetah. The cheetah, being much faster, represents viscous forces. The snail, representing surface tension, is slower. A high capillary number would be like the cheetah winning, while a low capillary number would be like the snail taking the lead. But how do we calculate this capillary number? It's actually pretty straightforward. The capillary number is determined by a simple formula, but its implications are vast and fascinating. Ca equals mu times u divided by gamma. This equation might look intimidating at first glance, but it's quite straightforward once you understand each component. Don't let the Greek letters scare you. Let's break it down step by step to see what each term represents and how they interact. Ka, our capillary number, the scorekeeper in this fluid dynamics game. It helps us understand the relative effect of viscous forces versus surface tension forces in a fluid. Mu. This represents dynamic viscosity, essentially the stickiness or thickness of the fluid. Think about honey, which has a high mu, versus water, which has a low mu. The higher the viscosity, the more resistance the fluid has to flow. U. This is the velocity of the fluid, indicating how fast it's moving. Imagine a river flowing swiftly versus a slow-moving stream. The faster the fluid moves, the higher the velocity. Gamma. This stands for surface tension, the clinginess of the liquid molecules to each other. Think of water, which has a high gamma, versus soapy water, which has a low gamma. Surface tension is what makes water droplets form beads on a surface. So the formula basically says capillary number equals the product of viscosity and velocity, divided by surface tension. This means that the capillary number is a balance between these forces. Higher viscosity or velocity will increase the capillary number, indicating that viscous forces are dominating. Conversely, higher surface tension will decrease the capillary number, showing that surface tension forces are more significant. Understanding this balance is crucial in fields like microfluidics and enhanced oil recovery. Now that we understand the formula, let's dive deeper into what different capillary numbers actually mean for how fluids behave in various scenarios. The capillary number, often denoted as K, is a dimensionless number that characterizes the relative effect of viscous forces versus surface tension forces in a fluid. This number can tell us a lot about the behavior of fluids in different environments. High capillary number, Ka much greater than 1. Remember the cheetah? A high capillary number means viscous forces are much stronger than surface tension. The fluid flows easily, even if it encounters obstacles. Think of pouring honey. It's thick, but it still flows. In practical terms, this means that in industrial processes where high viscosity fluids are used, understanding the capillary number can help in designing equipment that ensures smooth flow and efficient processing. Low capillary number, Ca much less than 1. This is the snail's time to shine. A low capillary number means surface tension is the dominant force. The fluid tends to beat up, resist spreading, and form droplets. Think of dewdrops on a spider web. In nature, this phenomenon is crucial for plants and insects that rely on the formation of droplets for hydration and other functions. In technology, it's important for applications like inkjet printing and microfluidics, where precise control of fluid behavior is essential. The capillary number helps us predict how a fluid will behave in different situations, which is super helpful in many fields, from manufacturing to medicine. For instance, in medical diagnostics, understanding fluid behavior can improve the design of devices that handle small volumes of biological fluids. In manufacturing, it can optimize processes involving coatings, adhesives, and more. So the next time you see a fluid in action, remember the capillary number and the fascinating science behind it.